Hi everyone, welcome to another video on sample size planning. This is our fourth video in a series that's part of the sample size planning workshop hosted by the North American Society for the Psychology of Sport and Physical Activity. These videos are meant to be kind of an asynchronous complement to a lot of the in-person activities that are happening at the workshop. So you can catch up on these things after you've gone through the workshop, or even if you've never attended the workshop, hopefully these videos will be helpful as you think about different ways to do a power analysis and figure out what sample size you need in order to run a well-powered study. So as a reminder, we're working through an example that was published in the Psychology of Sport and Exercise by Daniel Cabral and colleagues, where they had participants learning a motor skill and training either with the expectation of teaching or with the expectation of being tested on that skill later, and then seeing how, after practicing under those conditions, how well did those participants do under low and high pressure tests. So let's scroll down just to remind you a little bit about their design, right? Because in our previous video, we started with just simulating the difference between low and high pressure tests. And we looked at this as just a basically paired samples t-test. Ignoring the groups, if we just wanted to compare low to high pressure, based on the data we saw in this study, we walked through a simulation about how many people do we think we would need in order to replicate the choking under pressure effect, right? In order to show that people actually do worse under a high pressure test compared to a low pressure test. In this video, we're going to make it a little bit more complicated, although we're not going to quite go through their full design, because now we're going to consider the interaction between your group. Did you train with the expectation of teaching, or did you train with the expectation of testing? And if it's a low or high pressure test. So we're looking at this within versus between subject factor interaction. So essentially we're looking at a mixed factorial ANOVA, but we're going to have an additional wrinkle in which we control for pre-test performance for each individual. So this would be a mixed factorial ANCOVA, essentially, which is more or less what the authors did in their analysis. They had an extra factor of training with analogical instructions versus training with explicit instructions. We're going to tackle that in our next video when we take it all the way up to a 2x2x2 design, considering, teach versus test, analogy versus explicit, and low versus high pressure while controlling for pretest. So this is a very complicated design, already. So again, we're doing this in steps. In our previous video, we looked at low versus high pressure. Now we're going to look at the 2x2 design, but we're also going to control for pretest. So just to look at where we're going to get some numbers for this example, these authors very helpfully provided details about their statistical analysis and all of their data on the Open Science Framework. So I was able to go to their Open Science Framework repository, and then I downloaded their data for statistical analyses, which you can see here. And then doing a little bit of extra calculation, I was able to figure out, okay, well, what are the means on the pretest? What are the means on the low pressure test? And what are the means on the high pressure test for each of these different groups, right? And again, we're kind of ignoring analogy versus explicit instruction for now, and we're just focusing on teach versus test, and then low versus high pressure, but we are going to control for pretest. So we're really worried about these numbers here and these numbers here. And I'm going to feed these into some R code that I've written in order to simulate this design several thousand times in order to get some estimates of statistical power. So again, if you were actually doing this, right, you probably wouldn't want to copy exactly what the authors have put in because there's known publication bias. So you probably would want to scale these effects down in some way or enter means that you thought would be, kind of the smallest effect size of interest. But for the purposes of illustration, I'm going to be entering means based on exactly what these authors found. So if we assume that this is kind of the truth, then we can power our study for that. So let's come back to this R script. And again, the actual code is linked in a GitHub repository that's in the video description. So you can open that code and follow along if you're familiar with R and RStudio. But we're going to load a few packages that we installed in the last video. And then we're going to create some data first for our expecting to teach population. So again, we're going to simulate a population for each of these groups based on the descriptive statistics from the Cabral et al. Paper. And then we're going to repeatedly sample from those populations in order to create several thousand, pseudo experiments. So first, let's set the seed to make sure that when we do something using a random number generator, we get reproducible results. I'm then going to set the size of my expecting to teach population. I'm going to create 1,000 individuals. This could be bigger, but I think for a simulated population, 1,000 is probably fine. What we're really going to worry about more is the number of samples that we take, and that's where the actual size of the number of iterations of our simulation is a bigger concern. Next, I'm going to create a vector, which I'll call teach mean vector, and these are just my means. And they're going to go in order, so it's going to be the pre-test, then the low pressure test, then the high pressure test. And again, these are the means from Cabral et al. And then I'm going to create a correlation matrix. So this again is going to follow the same order as my vector of means. So the first column will be pre-test, then low pressure, then high pressure. So on the diagonal, all of those will be ones because that's low pressure correlates with itself perfectly. Or sorry, pretest correlates with itself perfectly, low pressure correlates with itself perfectly, and high pressure correlates with itself perfectly. And then I've built in an auto-regressive correlation structure where I said, okay, low pretest correlates with low and high pressure at about 0.6, right? So you can see that there and here. But low and high pressure correlate with each other a little more strongly because those occurred more closely in time. So I'm going to say those correlate with each other at about 0.8. And again, if you're actually doing these sample size calculations, you'd probably want to pick a few different values for these correlations, a few different values for the means, so you could understand what sample do you need across various different assumptions. So this is just one set of assumptions for how correlated we think these tests are in reality. And then I also need to create a vector of standard deviations. And so again, these are from the data from Cabral et al., right? These were just the standard deviations for this group on each of those tests. And then I'm going to do a little bit of matrix multiplication in order to convert these correlations into a covariance matrix by multiplying the standard deviations by the correlation matrix. Right, and then I have everything I need to use this MVR norm, which stands for multivariate random normal, in order to generate simulated data. And that requires 3 arguments. First, it needs the size, right, the number of observations we're going to create. It needs to know the vector of means, and then it needs to know the covariance matrix in order to have the appropriate distributions and relationships among our 3 different sets of observations. And we can see that a little more clearly after I simulate that by looking at the head of this object called teach distribution. And now you can see I've got 3 different columns. So this is my pre-test, my low pressure test, and my high pressure test. And then this is just showing observations for the first 6 individuals. But again, the key thing is these columns are going to have a mean and standard deviation based on what I programmed in before, and they're also going to have a correlation relative to each other based on what I programmed in before. Now, this is just a matrix, so I really would like to turn this into a data frame or a tibble, right, which is a tabular sort of object in R. So I'm going to feed the teach distribution into the as tibble function. I'm going to create a new variable called group, which will just repeat the values of teach, because again, all of these simulated people are from the population of people who practiced with the expectation of teaching. So essentially, I just want to associate all of these numbers with the word teach, because all of these would be theoretical people who practice with the expectation of teaching. And then finally, I'm going to rename my columns because, okay, 1, 2, 3, that's not very descriptive. Let's call that, pre-test, low pressure test, and high pressure test. I'm going to get a little warning here, it looks like, because the argument as tibble.matrix. Oh, it must have unique column names. So this is just a warning. It's not actually an error, but let's look at the head of teach distribution. I think it's just a little upset because I didn't actually have unique names for each person, right, in each column, right? They just have row numbers. So that will be okay. We're actually going to assign subject identifiers further down. This did what it wanted, but it is good anytime you get a warning message. Double check your data, make sure it is actually doing what you want it to do. Okay, and then next I'm going to gloss over this part pretty quickly because it's exactly the same set of code. The only difference is now we're doing it for a population of people who expected to be tested rather than who practiced with the expectation of teaching. So this is exactly the same. I'm only going to change the means and the standard deviations based on the data that were observed in the Cabral et al. Study. If you were doing this on your own, though, you could also theoretically change these correlations if you expected the correlations to be different between your different groups. For our purposes, however, I don't really expect the correlations between the tests to change. I just expect the means and the standard deviations maybe to be a little bit different. Okay, so once we have our two populations, right, we have our teach distribution and we have our test distribution, which each have 1,000 observations of 4 variables. Now we can actually sample from those distributions and then do our statistical test, right? Which in this case, for the Cabral et al. Study, we're really interested in the interaction between test, is it low pressure or high pressure, and group. Did you practice with the expectation of teaching or the expectation of testing? So to do that, I'm going to take 2 samples. I'm going to sample from my test population, and then I'm going to sample from my teach population, and then I'm going to use the row bind argument to basically stack those 2 samples together and end to end to create one data set. So you can see I've taken 2 samples of size 10, and now when I've row bound those together, that's 20 total observations because each row is a theoretical person. And so now this is what it would look like, in theory, if I did a small experiment where I had a total n equal to 20 with 10 people randomly assigned to the test group and 10 people randomly assigned to the teach group. Now, I'm going to mutate this a little bit because I want these data to actually be in long format. So the first thing that I'm going to do is I am going to use row names to columns to create actual subject IDs. So rather than just row numbers, I'd like this to be, subject number 11, subject number 12. So I'm going to use row names to columns to create actual subject IDs. And then I'm going to use pivot longer to melt those columns from low pressure to high pressure. So rather than having 2 separate columns, what I would like is multiple rows per person, where they've got a low pressure row and a high pressure row. So I'm going to melt those data into long format. And now you can see this is what my data look like. For each person, I've got 2 rows. They have a low pressure outcome and a high pressure outcome. Their pretest is the same, right? Because pretest is a static variable, so it stays the same across both rows. Group is a static variable because it stays the same across both rows. But test is a dynamic variable because I have a low pressure test and then a high pressure test within each person. And here is the actual score, right? The radial error of their putting score on that each respective test. Now, once we have the data in this format, we can actually build the statistical model that we want and then extract p-values. So in this case, I'm going to use linear mixed effects regression. Like I talked about in the last video, you could do this with ordinary least squares regression. You could do this using the AOV function for ANOVA inside of R. You could do this with whatever statistical test is appropriate for your research question. Across these videos, I've chosen to use a factorial mixed effect regression because it will give us the same answer as a mixed factorial ANOVA, but it is a little more flexible as a method of analysis. So I like to do this using a mixed effects model, which I will run now. So I'm going to create this object called mod0, where you can see I've got score as my outcome, pretest as a covariate. I'm going to look at the effects of group, test, and their interaction, because if you use this little asterisk in R, right, that gives you the factorial combination of those parameters. And then I'm going to have a random intercept of subject to account for the within subject nature of the test variable. So because I have multiple observations per person, I need that random intercept of subject. And now we'd have a few different ways of evaluating this. You could use, like the capital A ANOVA function. You could use the summary function. I'm going to use the little a ANOVA function because, as you can see, capital A ANOVA, although it does give us type 3 walled chi-squared tests, for chi-squared, it's a slightly different statistic, although it's related, obviously, to the F statistic, and therefore a slightly different set of p-values that we're going to observe here. But what I would prefer to actually have these f-values, because that gives us a closer correspondence to the actual mixed factorial ANOVA that you might run like in another software program. So I'm going to use little a ANOVA. And as long as you have the LMER test package installed, you're going to get p-values. Remember that LME4 by itself does not provide p-values for these things, but we want to use LMER test as a supplemental package that will use Satterthwaite's approximation in order to give us p-values based on the degrees of freedom here. So we can see that we get a complicated output because we've got sums of squared errors, mean squared errors, right, all the way down to p-values, and we have it for our covariate, our main effective group, our main effective test, and the group by test interaction. So if I just wanted to pull out individual p-values, right, I have to remember that this model object is a list. And so for instance, if I want the covariate p-value, I have to look at the sixth item in the list, right, which is our column of p-values. And then I need to pull out the first item from that list. Right, so this is our kind of complicated list subsetting in R using the square brackets. But this allows me basically to pull out all of the p-values that I want individually, which is really helpful because I'm going to want to store those things across my different simulations in order to estimate statistical power. Finally, much like we did in my previous video, we also maybe want to pull out a few descriptive statistics. So I'm going to, again, do a little bit of manipulation of this data set in order to calculate a difference variable to get the difference between the high and the low pressure test. And then across the different groups, I'd like to be able to save the average and the standard deviation on both the pretest, the low pressure test, the high pressure test, and the average and the standard deviation of the difference between low and high pressure. So if I do that, you can see I get this tibble where now I've got a bunch of different columns for the descriptive statistics that I'm interested in. And then I have one row showing me exactly what those values are. Oh, and sorry, they're mutated to pivot wider by group. This just makes it a little bit easier within the for loop. So this is the pre-average for the teach group and the pre-average for the test group. You could do this with like two rows, one for the teach group and one for the test group, but I chose to spread these out to be in a wider format just to make it a little bit easier to store these descriptive statistics in the for loop we're going to create down below. Okay, so now we're actually going to get into the meat of doing this simulation. We've shown you how to create the populations that have the relationships and the means and the standard deviations that you want. We've shown you how to run, an example statistical model and pull out the p-values and the descriptive statistics that you want. And now we're actually going to do this a bunch of times in order to get some estimates of statistical power. So I'm going to set my number of, or my sample sizes. So this is I'm calling this ends, and it's going to be a vector that goes from 30 up to 100 in steps of size 10. So this is going to be the number of people per group that we want to sample. So you can think about this as, we're going to start with a minimum of 30 people per group, and we're going to go all the way up to 100 people per group, and we're going to do this in steps of size, 10. So 30 is probably a good starting place with a between subjects design. It's seldom that if you have a between subjects factor, you would need fewer than 30 people in order to see the effect, unless it's a massive, massive effect. But again, you could make this as small of a starting value as you want. And we're going to go up to 100 just for ease of efficiency, because you could set this again as high as you want, but the bigger you make this range, the longer it's going to take this simulation to run. So one option would be always you could make this range big, but only do it in very large steps. And then kind of once you see critical power values, maybe you zoom in and you focus on some of those. But for instance, we wouldn't want to make this, some huge range where I say, well, let's go from like 10 to 10,000 in steps of 10, because now I'm going to have a massive number of simulations that I have to run. It's going to run very slowly, and I could probably do that a little bit more efficiently. So let's just go from 30 to 100 in steps of 10 for now. And then at each of those sample sizes, I have to set the number of iterations that I would like to see. And again, if you're setting this up for the first time, you might do a small number of iterations just to troubleshoot your for loop, make sure it runs quickly and it gives you kind of the answers that you want. So, if I was doing this for the first time, I might set this to something like 10. If I was doing this to be very, very confident, once I knew everything worked the way it was supposed to, and now I want to really make sure I'm converging on the correct kind of the best estimates of statistical power, I might take this up to something like 1,000. So I'm going to run 1,000 experiments at each individual sample size. Again, that's going to really slow down your loop, the more iterations that you're actually putting it through. So let's just say 200 for now. I think that will be good enough to probably get a relatively stable estimate, but also run fast enough that I won't have to sit here for a long time as we go through this video. So let's go ahead and create our vector of n's. We'll set k equal to 200. And then what we'll do is initialize a blank data frame called sim data. So it's just going to be a bunch of NAs, and it's going to have a number of rows equal to the length of our n vector times k, right? Because each row is going to be one of our simulated experiments. So for every n, I'm going to have k rows. So if I do this, I'll end up with the correct number of rows, which happens to be 1,600. And then in the next step, I'm going to do a little bit of renaming of my columns because, again, when I initialize this empty data frame, it's just going to have columns named things like x1, x2, x3. So I'd like x1 to actually just be the n value, which is where we'll save the size of the sample. An iteration value, which will tell us like, okay, at samples of size 30, this is the first experiment or the second experiment or the third experiment. And then I'm going to have columns to which I will save all the p-values from our mixed effects model. And then I'm going to have a bunch of columns where I save our descriptive statistics. And again, these descriptive statistics aren't necessary from the standpoint of doing the power calculation, but if you really wanted to be able to dig into these data later and have some things about, what did the distribution of low pressure test scores look like? What did the distribution of difference scores look like? It might be worthwhile saving all of this information from your simulations so that you can look at it later. But again, from just a power perspective, you could probably run this a little bit more efficiently if you just focused on the p-values, or indeed even just the p-value that you're really interested in. For illustrative purposes, however, I'm going to pull out all of these p-values just to show you, especially at the end, statistical power is very contextual. And just because I have an adequate sample size for one test doesn't mean I have an adequate sample size for all tests. All right, so we'll go ahead and rename all of those columns. And then we're going to get to the actual meat of the script here on line 120. I'm going to set row equal to 0. I'm going to set the seed equal to 1 because, again, we're going to have a stochastic process. So if we want this to be reproducible, we need to set the seed before we start. And then I'm going to implement the for loop. And the for loop is going to do exactly what we did above in terms of taking a sample and doing a statistical analysis, but it's just going to do it at each sample size, and then it's going to do it 200 times at each sample size. So let me go ahead and get that running, and you'll see that this is going to take a second to run. So I'll post like the actual total time it takes at the end of the video. But just to back up for a second here and talk you through the loop, this is really exactly the same thing we did in the previous video where we were looking at a within subject effect of low versus high pressure test. But the difference here is now when we take this sample, we have a teach sample and a test sample. And then when I'm going to bind those together, what I can ultimately do is test this group by test type interaction. Because Cabral et al. Were really interested in the interaction between expecting to teach and low versus high pressure, right? So this interaction is what we're really interested in here. So our model has gotten more complicated, right? We've had to do a few extra steps in terms of the simulation of the data, but at the heart of it, the principle is exactly the same. We're trying to simulate a population that has some characteristics we think might be true. We're going to sample repeatedly from that population, and we're going to do our statistical test a bunch of times, and then we're going to save the results of that statistical test. And once you kind of master those fundamentals, you can actually do a sample size approximation for all kinds of studies, even with very complicated designs. And that's really helpful because it can sometimes be difficult to find a closed form solution for a complicated design. Like if you've got a 2x3x2 interaction, for one thing, you might want to consider simplifying your design. But for another thing, it's going to be really tricky figuring out, well, exactly what is the correct standardized effect size for that? And okay, exactly how do I control that in some other power calculator? What if I wanted to control for a certain covariate? And now how much residual error do I think that covariate will account for? Right. So I think there are a lot of things that can get confusing, especially when you're trying to use power calculators that really rely on math to crunch the numbers. But if you understand some of the fundamentals of simulation, then you can really create a pretty complicated version of reality, and then say, okay, well, what would the data look like if that were true? And remember, that's the fundamental point of statistical power. We make some assumption about what really might be going on, and then we say, okay, if that is true, what proportion of our results will be statistically significant? Because statistical power is the proportion of results that are statistically significant, given that some real true effect exists. So once you get used to being able to simulate that kind of alternative reality, you can calculate statistical power very easily, right? And then what you need to do is think about, okay, well, what if my guess about reality isn't quite right? What if the effect size is smaller than I think? Well, you can go back and enter different means. What if the variance is a little bit bigger than I think? Well, then you can go back and enter bigger standard deviations. What if I control for this extra covariate? Well, that probably depends on exactly how correlated that covariate is with other variables, and you can control that when you're running your simulations. All right, so our loop has finished running, and now we have 1,600 times through that loop. We've taken samples and we've calculated the results. Again, if you really wanted like a very concrete answer and you wanted to make sure you had exact estimates, you might take that number up to like 500 or even 1,000, but just be prepared that you'll probably be sitting at your computer for a little while longer. But for our purposes, I think 200 will be a reasonably good approximation of statistical power for each of these cases. Next, I'm going to summarize all of this simulated data because, again, if I just look at it, it's a lot, right? Okay, here's my first sample with 30 people in each group, and then I had experiment 1, experiment 2, experiment 3. You can see the p-values that we get from each one. You can see the descriptive statistics that we get from each one. That is a lot to look at. And we probably want to, have something a little bit easier to work with than that big spreadsheet that's 1,600 observations long. So to do that, I'm going to create a new object called SimSummary. So I'm going to push that simulated data through the group by function to group it by sample size, because this is our n per group. And that's kind of what I'm most interested in looking at. I'm not really interested in the individual experiments, but what I would like to know is for 30 people per group or 40 people per group, what proportion of the covariates were statistically significant? What proportion of the main effects were statistically significant? And what proportion of the interactions were statistically significant? So that's what I'm going to calculate here using the summarize function. And then I'm going to pivot that to be a long format file to make it a little easier to graph. But let's go ahead and just run this code, and then let's print SimSummary to the screen, just so you can see it. So you can see there are 22 rows that have been omitted, but you can see our 3 columns, right? The sample size per group, the particular effect that we're looking at, and then the estimated statistical power for each one. And so again, that's the proportion of these effects that were statistically significant at that sample size. So when we had 30 people per group, basically our covariate was statistically significant every time pre-test was related to the post-tests. Group was statistically significant about 46% of the time, test type 34%, right, and the interaction about 30%. So 30 people per group, pretty low, not good news for statistical power. If I take that up to 40 people per group, you can see that it gets a bit better, right? But, this table itself might be helpful, but down below, what might really be helpful is if we actually plot some of this data so we can get a nice, easy visual summary of the statistical power in each of these cases. So given the data from Cabral et al., if we accept that as reality, which again, maybe is not the best thing to do, and we should probably try a series of different parameters when we do these simulations. But if we accept Cabral's means and standard deviations as the truth, right? This is our statistical power across a range of different sample sizes. And you can see now that our ability to detect different effects changes as a function of the sample size. So our covariate always has good statistical power. It's very easy to detect the relationship between pre-test and post-test. In terms of the difference between groups, now controlling for baseline, this group main effect, we don't really hit 80% statistical power until we get about 60 people per group, up to about 70 people per group, right? And so again, this is a situation where I might increase the number of iterations or increase the number of steps to get a more specific answer about the sample size here. But you can see, all right, once I hit, maybe let's say 60, it looks like I'm in pretty good shape to detect the group main effect. However, I'm not still in great shape to detect the main effect of test type, right? That difference between low and high pressure tests. And I'm in even worse shape to detect the group by test interaction. And those of you who are familiar with statistical power probably know this already, right? But it's almost always going to be harder to detect interactions than it is to detect main effects. And we'll see this especially in the next video where we go through the more complicated design. But as you add factors, right, it really depends now on what is your hypothesis. If we were thinking about the main effective group and that was our goal, we might need a very different sample size than if what we're really trying to show is that there's a group by test interaction. And if that is our goal, it looks like, well, we actually need quite a few more people, maybe even more than 100 people per group. And I might have to rerun my simulations, with a larger sample size on the high end until I can actually find, exactly what it is, what n per group I need in order to achieve 80% statistical power or 90% statistical power, etc.